Hello everyone, this is Dr. Bilal. In this video, I will talk about the tacticity of polymers. So, what is tacticity? Tacticity is the special arrangement of monomer units in a polymer chain. Special arrangement means the three-dimensional organization of atoms, groups, or side chain along the polymer backbone. Now, let us understand why tacticity arises. For this, let us take an example of symmetric molecule. Which means a molecule in which same type of groups are present on both sides of a double bond, like ethylene or tetrafluoroethylene. In this case, when the polymer is formed from these types of monomer, they can add to the growing polymer chain only in one way, resulting in a linear polymer as shown here. But in the case of non-symmetric molecules, this means a molecule in which different types of groups are attached on each side of the double bond. This means all the monomers of the type CH2 double bond CHR, where R is a substituent or branch. Examples of these types of monomers are styrene, propylene, and vinyl chloride. During polymerization of such monomers, there are two possible orientations for any new monomer to covalently attach to the growing polymer chain, as shown here. This means the side group of the monomer can be below or above the plane. This is how tacticity comes in. So, the tacticity of polymer describes the orderliness of the R group in a polymer chain relative to the polymer backbone. Based on the arrangement of side groups, polymers can be classified into three main types. Isotactic polymers. In these polymers, all the side groups are arranged on the same side of the polymer chain. Either the all side groups are above or all side groups are below the plane. This regular arrangement often leads to high crystallinity and strength. Syndiotactic polymers. Here, the side groups appear in an alternating pattern along the polymer chains. This alternating pattern can also contribute to crystallinity but in a different structure compared to isotactic polymers. They have low crystallinity than isotactic polymers. In atactic polymers, the side groups are arranged randomly along the chain. This random arrangement usually results in amorphous, less crystalline material that might be softer and more flexible. Crystallinity is an important property in polymers, as the crystallinity in polymer affects their mechanical strength, thermal stability, and chemical resistance. High crystallinity typically leads to stronger, more durable materials. This means that more crystallinity leads to better quality of polymer. This means isotactic and syndiotactic polymers are important material for practical applications. But the problem is how to guide the monomer to enter into the growing polymer chain in the same orientation. This was a mystery until the Ziegler-Natta catalyst was discovered. The history of Ziegler-Natta catalyst is also interesting. Carl Ziegler was a German chemist trying to improve the quality of polyethylene. The polyethylene synthesized at the time was a highly branched polymer, the synthesis of which required high temperature up to 300 degrees Celsius and a pressure up to 3000 atmosphere. But still, the polyethylene obtained had low quality, low density, and low crystallinity due to the presence of branching that hindered the mobility of the chain to crystallize and had limited mechanical strength. Ziegler used a combination of triethyl aluminium and titanium tetrachloride as a catalyst to form polyethylene chain that were longer and had fewer branches, and crucially could achieve this under less intense temperature and pressures than the method used at that time. The resulting polyethylene was high density polyethylene with high crystallinity and mechanical strength. Ideally, polyethylene should look like this. It should be without branching, hence show high crystallinity, but it is very difficult to achieve. Later appeared another chemist from Italy, Giulio-Natta. Inspired by Ziegler's work, he applied similar catalysts to polymerize propylene. He discovered that the catalyst could control the stereochemistry of polymerization process, as it was designed to favor the insertion of propylene monomer in a way that maintains the same spatial orientation of the methyl group, leading to the formation of isotactic polypropylene, where all the methyl groups are arranged on the same side of polymer chain. This regular arrangement gave the polymer high crystallinity, strength and thermal stability. Since Natta's work expanded the scope of Ziegler's catalyst to include stereochemical control in polymerization, it was recognized as Ziegler-Natta Catalyst. Ziegler and Natta were jointly awarded the Nobel Prize in Chemistry in 1963 for their discovery. Now let us see how tacticity affects different properties of polymer. Isotactic polymers are highly crystalline due to their regular chain packing. Syndiotactic polymers are also crystalline but less than isotactic polymers because of their alternating arrangement. Isotactic polymers have high melting point due to strong intermolecular forces and an ordered structure. Syndiotactic polymers have a moderate to high melting point, which is lower than isotactic but higher than atactic polymers. Isotactic polymers shows high mechanical strength due to their crystallinity and strong intermolecular interactions. Syndiotactic polymers have moderate to high mechanical strength, which is less than isotactic but more than atactic polymers. Isotactic polymers are rigid due to their high crystallinity. Syndiotactic polymers are moderately flexible, more so than isotactic but less than atactic polymers. Solubility. Isotactic polymers have low solubility in most solvent because of their high crystallinity. Syndiotactic polymers have moderate solubility, higher than isotactic but lower than atactic polymers. Isotactic polymers are typically opaque or translucent due to their crystalline regions. However, syndiotactic polymers are translucent and generally less opaque than isotactic polymers. Isotactic polymer required precise polymerization conditions such as Ziegler-Natta's catalyst or metallocene catalyst. Syndiotactic polymers require specific catalyst and conditions to achieve their alternating arrangements. Isotactic polymers are used in high-strength material, fibers and films such as ropes and packaging. Syndiotactic polymers are used in specialty plastics and films where moderate crystallinity is desired. Now the question is how to measure tacticity. Measuring the tacticity of polymers is crucial for understanding their properties and behavior. Here are some common methods used to determine polymer tacticity. Nuclear magnetic resonance spectroscopy. In NMR spectroscopy, we can determine the tacticity of a polymer using proton or carbon-13 NMR spectroscopy. The proton NMR spectroscopy analyzes the hydrogen atom in the polymer chain. By examining the chemical shift and splitting pattern, we can determine the arrangement of side group and calculate the tacticity. The carbon-13 NMR method focuses on the carbon atom in the polymer backbone. It provides detailed information about the stereochemistry of the polymer, allowing us to distinguish between isotactic, syndiotactic, and atactic sequences. The other way of finding tacticity is X-ray diffraction. In the XRD, the diffraction patterns provide information about the regularity and arrangement of polymer chains, which can be correlated with the tacticity. Later in some video, I will show you with detailed examples how one can calculate tacticity using these methods. Thanks for watching. If you find the video helpful, then please share and subscribe.